Welcome to SanfordFlipMath. This is AP Calculus. We are working, as you know, through the Finney, Demana, Kennedy book. We are starting, dare I say it, Chapter 6. I'm kind of excited. We have this chapter and one more chapter to go. And this chapter is about differential equations. Differential equations are basically equations that, shockingly enough, involve differentials. And differentials, as it says here, and we've talked about, is basically derivatives. So if you have an equation that involves derivatives, like for instance, maybe we have something like dy dx equals 2x plus 3, that's a differential equation. Or maybe you have something like x plus y prime minus x prime equals 3, that's a differential equation. The solution of a differential equation is any equation that doesn't have derivatives or differentials that would produce the same differential equation. Okay, so when we talk about solving differential equations, what we're trying to do is basically undo derivative, which will involve antiderivatives and things like that oftentimes. Okay, a specific topic in differential equations is slope fields, and that's what the basic focus of this video is going to be about, is slope fields. We're going to do just a tiny bit of finding solutions of differential equations analytically first, and just so we kind of have an idea of where we're going with this, and then we'll play around with slope fields. So, all right, so slope fields, I'll say more about it in just a minute, but basically it is a graph of tiny little segments, little chunks of slope based on the differential equation, and the goal is so you can kind of see the shape of what the solution equation would be. You'll see what I mean in a minute. Okay. First up, what I'd like to do is we're going to just take a minute and solve a differential equation, and we're not going to spend a lot of time on this, but let me just kind of emphasize the first thing we're going to do is separate the variables. Okay, so separate variables, and so we want anything about x on the one side and anything about y on the other. So I'm just going to multiply both sides by the dx. And so I have dy equals 2x dx. Okay, so this is, we're just separating the variables. We want all the y variable on one side and all the x variable on the other side. And then to get rid of the d stuff, we're going to do antiderivative. Okay, so the antiderivative of dy is y. The antiderivative of 2x would be 2x squared over 2, which we can then simplify. And the only other thing that we need to really do here is something we're not used to because we've done so many definite integrals with limits of integration and stuff, is we have to remember that we need to go back to the c. So this is y equals x squared plus c. Okay. Now, one tiny little thing that relates to this, and that is if I have an initial value, some kind of a value for x and for y, then I can actually find c. And that's what I had sneakily hiding down here. So worth noting that I can just take this same exact equation I had, because this is the same differential equation. Again, dy dx equals 2x, that go back to the top. That's the dy dx equals 2x, same equation. The only difference is I'm telling you an initial value. And so this is f of x equals y. So I have an x and a y value here, and I can actually substitute in the y value 0 and the x value 1, and I can solve for c. So this is going to be 0 equals 1 plus c. Subtract 1 from both sides. C is negative 1. So that means that it's really y equals x squared plus negative 1, or in other words, x squared minus 1. So I was actually able to find the specific solution once I knew this. And since it is f of x, I could write, and it's not a big deal, I could write that. Okay. Now I know that's one little speedy example, but what I want to do then is take this same dy dx equals 2x, and what the heck is that? Yeah. All right, so what we're going to do is what's called a slope field. Slope field, and then we're going to connect it back to what we just did. Okay, and the reason we're doing it with this simple equation is because sometimes equations aren't simple. You know, I can do an antiderivative of this. I can even go back and find the constant if I have an initial value, a point to work with, but sometimes it's not that cute. Sometimes it's just downright ugly. Okay, so we're going to do what we refer to as a slope field. And again, a slope field is a graph of segments with slopes that are based on the differential equation used to show the basic shape of what that original function would have been. Okay, so in other words, I'm going to take x and y values and put them into this thing to find dy dx. Okay, so what I'm going to do is let's focus on, now we're not going to do this whole graph, and you'll see in a minute why. We're just going to maybe do this much of it. Okay, so from -2 to 2 both ways. Okay, and imagine these dots as points like ordered pairs. So like this is 0, 0, and this is 1, 0, and this is 2, 0, okay, etc. Okay, so we're just numbering by ones, and all we're doing is then we're going to put in the values in here. So for instance, x, y, and I'll do dy dx. I'm going to do just a quick little table, and as we're doing this, we'll graph things, okay? So like when I put the ordered pair 0, 0 in, I put x for x and y for y. Well, there's nowhere to put a y, so I'm just going to say 2 times x, 2 times 0 is 0. So that means the slope at this point is 0. And notice what I'm doing is a tiny little mini slope. Okay, let's go to the next one right here. Okay, so 1, 0. Okay, so 2 times 1, okay, I'm putting in the x value here, 2 times 1 is 2. So for that point, I'm going to have a slope of 2. So I'm just going to kind of picture in my head that that's going to be steep, you know, steeper. It's got to go the slope in the positive direction. And imagine what we're doing. We're saying a slope rise 2 and a run of 1, so it's got to be that steepness. Well, that's me trying to eyeball that steepness. Okay? Okay, so let's do 2, 0. Okay, so that's this point. Okay, and again, it's 2 times x, so 2 times 2 is 4. So it needs to be steeper than the last one. Now, again, I'm not getting out a ruler. I just know it needs to be steeper. Okay, let's do -1 and 0, sorry. So now I'm doing this point. Okay, so now it's 2 times that x value, so 2 times -1. So -2. So it's going to look the same, only it's got to be going the other direction. Same steepness, but I don't want the direction the same because it's a negative slope. So the slope of this guy and this guy, same slope, just opposite directions. Okay. Okay. Well, I'm going to do, let's do one more in writing, and then I'm just going to start eyeballing stuff. Okay. So again, -2, 0, so that's this point. Okay, and so 2 times -2, -4. Okay, so again, -4. Okay, so again, steeper than the -2. Not vertical, but steeper. Okay. All right, we're going to do the same thing, only we got to move this along a little bit. Okay. So for instance, I'm going to do all of these points together. Okay, so here, this is -2, +2. Well, this is really only about that x value, isn't it? Okay, so for instance, let me, I got to put my red point back, sorry. All right, there we go. Okay, so -2, this x for this one right here, 2 times -2 is -4. For this point, again, it's still a -2x value, so it's still -4. Notice if all of these have the same x value, they're all going to have the same slope in this case because this differential equation is only about x. Okay. Okay, so sometimes if you notice things about the equation, like this is only about x, then we can focus on the x values and not worry about the y values. Okay, and that won't always be the case. Sometimes it's going to be about y. Sometimes it's going to be about both. So the level of thinking changes. Okay. All right, so here I'm at -1, 2, so this is going to be 2 times -1. All of these are going to have a slope of -2. Going down the y-axis, this has an x value of 0, so 2 times 0, 2 times 0, 2 times 0, 2 times 0, 2 times 0. 2 times, and now I'm going to go down the ones. Okay, so here's x equals 1, so 2 times 1 is 2. and then 2 times 2, so I'm going down these points. Okay? All right, so what you need to see out of this is, it's not obvious at this point, but the idea is that there's a definite flow to this, and if I like start and kind of just flow, so I'd have to go horizontal here, and then I have to start going up. So it, you know, if I imagine where a function would be going through this, it would have to look something like this. Okay, does that make sense? You know, think about, I'm following the flow, I'm following the, you know, through this field of tiny little slopes, and I mean, this is the first time you've ever seen anything like this. It looks kind of intimidating, but it's really not a big deal. There's a flow to it. Okay, now let me pop back just for a minute to this, and remember what this function ended up being. Well, it ended up being y equals x squared. Now, if I go back here, and again, let me go get my little highlighter going. Doesn't this look like some version of y equals x squared? Or if I was actually at y equals x squared itself, where the, that wasn't supposed to go straight, okay, then you know, you're seeing that parabola. Okay, now one more little distinction here. What if I say that we have to start at the point 1, 0? Okay, so this is now a slope field, and we're gonna have an initial value. So here's that point 1, 0. I'm going to draw that specific solution. Okay, so if I tell you it starts at 1, 0, and if I start at this point, then I'm going to go to the right. I have to go steeper and steeper and steeper, right? I need to be kind of parallel to these guys as I go through there. And then this is going to, I don't know, it's got to go something like that. Okay, so again, I'm following the curvature of what's going on. And this is not an exact science. I mean, it could be, but it's not. We're just kind of ballparking things, okay? And that should make sense with this, okay? So that's one example, and we'll do another. Okay, so, all right, so it looks really similar to the last example we did. Really the only difference is this one's about y. Okay, so I'm going to go ahead and start out with a little table again, just to kind of make sure we're clear as to what's going on, and then we'll kind of speed it up. And again, I'm just going to work between -2 and 2, both ways, both in the x direction and y direction. And you're going to see sometimes maybe you have to go from -3 to +3 both ways, or sometimes it might say go from -4 to 4 on the x direction and -5 to 5 in the y direction. It just depends on who's writing the problems and how much they think you need to look at. So I'm going to start again at 0, 0. And 2 times the y value 0 will be 0. Again, there's no place to put an x. And then we'll do like 1, 2, and we'll do some 0, 0. So again, these y values are all 0, and this is all about y, so this isn't terribly exciting. Okay, so what I just did was at 0, 0, here's a slope of 0. At 1, 0, a slope of 0. At 2, 0, a slope of 0. Well, I'm willing to bet money that anything with a y value of 0 is going to have a slope of, you guessed it, 0. Okay, all right, so let's do some more. Let's do, again, since this is all about y, we can kind of just focus in on the y values, okay? So for instance, if I go to 0, 1, well, 2 times this y value is going to be 2. If I go to 0, 2, 2 times that y value, 2 times 2 is 4. Okay, so here's 2, and here's 4. Now, and I know, I just want this to look a little steeper than this one, and I'm not getting out a ruler, I'm not checking, you know, every little detail here. 0, -1, well, 2 times -1 is going to be -2, and again, I'm doing 2 times the y value, and 0, -2 will be -4, same idea, okay? Okay, so this needs to be a little steeper than this one. Now, what's cool about this is, again, this is all based on the y value, okay? So since all of these y values are 1, then these are all going to be 2 times 1, or 2. The top row will all be 4, so a little steeper. Okay. underneath, these are now negative, 2 times negative 1, so negative 2, negative 2, negative 2, negative 2, negative 4, negative 4, negative 4, negative 4. Okay, now, so understand that the flow of this one is a little different, okay? So the higher you get, the steeper it is. So like, for instance, if I started out right here at 0, 1, as I go to the right, it needs to go steeper. Oh, I hate when that does that. There's probably a way to shut that off, but I don't know it. So, okay, let's see if I'll do that without, let's just do it with a regular pen. So something like that. And then as I go down, notice that these ones on the x-axis are actually horizontal. So I need to not, as I get closer and closer to the x-axis, it needs to stay close to the x-axis going horizontal. Okay, so that's an example of what one specific solution would look like. Okay, all right. So what I'd like to do then is take this for a spin symbolically. Dy dx equals 2y. All right, so I guess what we'll do is just kind of stick it in off to the side here. Okay, so dy dx equals 2y, and we're going to solve this analytically. Okay, so again, I need to separate variables. So I'm going to multiply both sides by dx. And now the problem is that I have this y in here, so I'm going to divide both sides by y. So now I have dy over y equals 2 dx. This black is probably blending with the black, so I'll switch. Okay, well, this, I'm going to do the antiderivative of both sides. And on the left side, this is probably not obvious because we've only worked with this a little bit, but here it is. And so again, this is. Now, antiderivative of 1 over something, if that something is just the plane, it's not like y to the negative 2. If it was y to the negative 2, I could do the power rule, but this is actually going to be the natural log of y equals. Now I need to do the antiderivative of 2 is going to be 2x, and then again we don't have limits of integration, so I need a plus c. Now technically there would be a plus, there'd be a constant on the left side and a constant on the right side, and they don't have to be the same constant. So what we do is just move all of those constants over to the right side so we don't have to worry about it. Okay. Now there's one other little issue here that is not obvious, and that is this. When you do an antiderivative of 1 over y, we actually have to do an antiderivative in here, okay, or 1 over x, even 1 over whatever. Okay, so a quick little note to self. If I'm looking at the natural log, sorry, I don't want natural log, I'm just going to say u. So if I'm doing the antiderivative of 1 over u du, it's actually not just the natural log of u, we're going to say the natural log of absolute value of u. And the reason is that the x or the y or the u could have been a negative value, and the domain for natural log or any log is only positive. So we're going to force this to be positive so that we can still use it. Okay. All right, well, we got a couple things to do to finish this last one up, and that is we need to solve for y. So you may recall that logs are about exponents, so this whole thing is an exponent. And so this becomes e to the 2x plus c, I know you don't like that, I'm sorry, is the absolute value of y. Now to get rid of an absolute value, you may or may not recall that you have to do a little positive or negative thing. And this would work. You could be done here, okay? Until you solve for y, you're not done. One other option is that it's probably worth noting that e to the c times e to the 2x is the same thing, and oftentimes if you get a constant, if you solve for the constant, you can actually figure out the number for that. Okay? All right, I don't want to deal with this initial value problem, so I'm just going to kind of ignore that it's there. Okay. Okay, and we're just going to do one more problem and call it good, and we're going to do dy dx equals x plus y, and the only reason is I want to make sure we do one that includes both x and y. Okay, so again, I'm going to focus in on this -2 to 2 both ways kind of thing in the middle, And I'm just going to go, I'm going to go across the axes first, and I'm just going to go 1 point at a time. So I'm going to start here at -2, 0. So -2 plus 0 is -2. Going across from left to right. -1, 0. Well, -1 plus 0 is -1, so not quite as steep. 0, 0. Well, that's going to be horizontal. 1, 0. It's going to have a slope of 1. 2, 0, 2 plus 0. And again, all I'm doing is adding x plus y. Okay? All right, I'm going to go up a row. Okay, so I'm going to start here at -2, 1. Well, -2 plus 1 is -1. This one is -1, 1. They add up to 0. 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. Now this is going to get a little tricky because, I mean, how steep do you want to make it and how steep can you, so just kind of understand what's going on, okay? Just do your best, okay? All right, one more row above, okay? -2, -2, I'm sorry, -2, +2. Again, this is coming from the ordered pair, -2, 2. So when I add those together, I get 0. So it looks like all along this diagonal, there's zeros. And when you can see patterns like that, it's going to make your life easier. Okay? So like for instance, this one was -1, -1, -1, -1. They're going on a diagonal because of the way the x and the y are having their little interplay. Now if that's confusing to you, you can always just stop and do just the x and y separately. Okay. Okay, so we're just going to keep right on going. And again, this was at, I'm going to deal with this point while I'm here. This point's at 2, -1, so 2 plus -1. Again, all I'm doing is the x value plus the y value. Okay, so that's 1. Okay. Okay, and so that finished that diagonal. Oh, here's another one of those. Okay, and so at -1, -1. Add those together, that's -2. Okay, and that'll follow that diagonal. Okay, at -2, -1, the steepness will be -3. And at -2, -2, the steepness will be -4. So it's hard to see the distinction, but so here's the slope of 0, -1, -2, -3, -4. They're getting steeper as we go that way. Okay. All right, let's finish the top. 0, 2. 0 plus 2 is 2. Okay. 1, 2. Oh, that's going to be 3. This will be 4. Okay, so that finishes that. Okay, so now some things to notice here. If we were going to draw through potential solutions, again, remember you have to kind of follow the flow. Then, for instance, somewhere like this, something like that. Okay, looks like through here, looks like there's probably some kind of a slant asymptote kind of thing that happens. So like over here, maybe we'd be doing something like that. Okay, and so I'm going to guess there's probably, one that's going straight through something like that. That would just be a line, which would probably be an asymptote for whatever this graph is. Okay, all right. So where are we with this? Well, I'd have to do a bunch of craziness to separate the variables. I'm not going to worry about it. But slope fields are not a hard concept. You just need to kind of sketch mini slopes all around. They seem a little tedious, but the idea is it gives you a picture of what the graph would look like even without knowing the antiderivative. Okay, and we'll leave it at that. And thank you much. And SanfordFlipMath for AP Calc. Bye. Oh, shout out to Alex. All right, there it goes. Whoop, whoop. Alex Swift. Yeah, oh, got to get the whole thing in.